Greetings everyone, my name is Rick Tonello. I'm the Chief Astronomer here at the Gravity Discovery Centre Observatory.
The Gravity Discovery Centre and Observatory is a non-for-profit science education centre with a focus on astrophysics, Einsteinian gravity and cosmology. Located approximately 80 kilometres north of Western Australia's capital city along the Wallingup Plain, the Gravity Precinct is nestled within pristine bushland, far enough away from the light pollution of Perth. The Gravity Precinct showcases a hands-on, interactive science centre where visitors can experiment and begin to understand the differences between Newtonian and Einsteinian gravity, how gravitational wave detectors work, and the nature of space-time. The Gravity Precinct also has the Leaning Tower of Gingin. This 45-metre high tower enables visitors to ascend the 222 steps to replicate Galileo's original experiments with falling objects. Also on site are 3 optical observatories. The Gravity Discovery Centre Observatory is Western Australia's premier public observatory. Here, visitors and students have the chance to observe through one of the largest telescopes for public use in Western Australia. The SpaceTime Simulator, also known as the gravity table, has the unique ability to help people visualize the curvature of space-time caused by the mass of an object. Granted, it leaves out one spatial dimension and the temporal dimension, the space-time simulator can demonstrate how the curvature, due to the mass of an object, can affect planetary orbits, how spacecraft use the mass of larger bodies for a gravitational boost, and how one gets spaghettified nearing the event horizon of a black hole. Its simplicity in construction is what makes it such an elegant tool for these types of demonstrations. The Gravity Discovery Centre's space-time simulator is made of 3 major components. The frame. Ours is constructed from the frame of an old trampoline. The frame can be constructed from timber to create a square or rectangular frame, or by cutting a circular hole through the top of an existing table. The fabric of space-time. We found the best material to use was lycra, also known as spandex. This material possesses the stretch quality and strength needed to create a curvature and spring back to its original flat shape. Test masses. The GDC employs a number of different size and mass spheres to demonstrate the curvature of space-time. For example, we have a solid iron shot put that can represent the mass of a star. We have a light aluminium sphere that represents the mass of a super-Jupiter planet. We have a billiard ball that represents a Jupiter-like planetary object, and a golf ball that represents a low-mass planet similar to Earth. Demonstration 1. Curvature of space-time affecting the path of a light photon. Famous physicist John Archibald Wheeler stated, "Matter tells space how to curve, space tells matter how to move." We see that the photon, represented by a billiard ball, will travel in a straight line, if there are no other gravitational distortions in the space-time fabric. We then add a large mass, an iron ball, enough to create a sizable distortion. We now observe the photon's path is affected by the geometry of space-time caused by the iron ball's mass. It alters its path. This is a great way to introduce the concept of acceleration, change of direction, and a good segue to describe how Einstein understood gravity. Demonstration 2. Planetary orbits around a stellar mass. Where Sir Isaac Newton developed a mathematical formulation of gravity which he described as an invisible force lashing the planets to the sun in their dutiful motions, Einstein saw a more elegant way to describe the motions of our family of planets. They followed a straight line along the curved geometry of space-time. Therefore, there was no force holding the planets to the sun, just the shape of space that kept them in their respective orbits. Demonstration 3. Gravitational Sling-Shot. We use two similar mass spheres to demonstrate how one sphere will utilize the momentum from the other to receive a gravitational kick, thereby causing it to be flung into a higher orbit and causing the other sphere to spiral into the center quicker. This is a great way to explain how spacecraft receive a gravitational kick or boost from planets, like Jupiter, to accelerate them further out into the solar system without the need for extra rocket fuel. Demonstration 4. Free return trajectory. With two similar mass spheres, one representing the Earth, the other representing the Moon, we can replicate the famous Apollo 13 saga that utilized this technique as a way to return the astronauts on their stricken spacecraft safely back to Earth. The gravitational distortion on the space-time fabric demonstrates, by following the curve, a spacecraft, with carefully timed firing of rockets of course, would fling the spacecraft back towards its point of departure. Demonstration number 5. Spaghettification. Using smaller ball bearings, we can observe, when released, the ball bearings form a single body traveling across the curved geometry of spacetime. However, as the body approaches the central mass, it becomes disrupted and the group stretches, or rather spaghettifies, to form a line of ball bearings as it spirals closer to the center. The most effective way to release the ball bearings and maintain a group structure is from a small cup that loosely binds the ball bearings together. Though this may not be practical and most probably very difficult to construct, the Gravity Discovery Center has a large form of SpaceTime Simulator that demonstrates the extreme curvature of spacetime near a black hole. This 4-meter high model allows people to observe tennis balls disappearing beyond their visibility, an event horizon if you will, never to be seen again. The SpaceTime Simulator is a cheap, easy to construct apparatus that utilizes materials and parts that can easily be accessed and purchased at a relatively low cost. Its effectiveness at demonstrating Einstein's principle that space and time can be affected by the mass of an object is easily understood by students of all ages.